Let's talk about how AI is used in today's robots. Now, first of all, what is hard in robotics? Safe interactions with humans, human-like dexterous manipulation, and navigating human environments is still grand challenges in robotics. So we'll focus on the third one. How does a robot navigate a human environment? Well, our environment is a map when you think about it. We make a lot of simplifying assumptions and we reduce everything to a two-dimensional map where there are obstacles, which are walls and furniture and so on and so forth, and there's free space for a robot to navigate. So it's in a sense a maze. So we can map the maze into a graph to represent. So a graph is basically, again, a combination of nodes and connected paths. Okay, so here's an example. The same graph, we took it and now we named the nodes. These are the locations of free spaces. And then if the plus sign on the map is the robot, we can basically search for the free space, go from node to navigate. Now, in more complex environments, these algorithms take more complex forms and shapes. We can imagine wave propagation, for example, and today's topic is on that Wavefront algorithm. But let's go back to the basics and let's first understand what is the control scheme for a mobile robot. What happens under the hood? Your readings will help you with this slide as well. But the idea is that when a robot is navigating in a real world environment, first thing is that it needs to collect data. It needs to sense. And usually our sensors produce raw data. From that raw data, we have to infer information. We have to convert it into models and maps. This is known as the perception block, which is the yellow block on the left-hand corner of the diagram. What is perception? What's the output of a perception when you take points, measurements, and convert them into lines and planes? That is the perception block. And then there's the map building and localization. A big problem or big question for a robot to answer is, where am I? Where is the environment? What environment am I in? And where am I in that environment? So that's known as the localization problem. Then once the robot figures out where it is on the map, and once it can see at least, for a foreseeable horizon in that map, it can act, it can calculate actions, and it can calculate paths to navigate. So sometimes that comes from a higher level. If there's a preferred way of navigating and so on and so forth, but that becomes the path planning algorithm. And then once the path is calculated, how do you execute it? How do you go from one point to another? Can you even go from one point to another? That depends on the low-level characteristics of the robot. And then a robot keeps doing this in real world continuously to navigate. So mobile robot path planning problem is identifying a trajectory that when executed will enable the robot to reach a goal location. So we have a start and we have a goal. To be able to achieve this, we need to have a representation. So we need to have a representation of the states, which is the location of the robot for our case. Actions, right? So how do robot move from one point to another? And then initial and goal states. And then the plan becomes a sequence of actions and states that achieve the desired goal state. In general, if we just focus on the path planning problem again, now you compute the path. Let's say, at a higher level, somebody tells you here's the map and here's the open space and so on and so forth. You compute the path, but then execution usually is not that straightforward. You got to smooth it. You got to make sure that the robot can navigate through that path. And then you got to design a trajectory, how long it's going to take, what is the velocity function, and so on. And then you have to have the low-level control. So this is this slide itself can be a completely different module, learning module. But then what are the fundamental questions when it comes to path planning? How is a plan represented? How is the plan computed? What does the plan achieve? And how do we evaluate the quality? For the sake of the examples in this module, you'll assume that the world consists of obstacles and free space, as we've seen one example already. But then we talk about, rather than free space, we talk about the configuration space for the robot. So this is the space of all possible robot configurations. If you worry about the orientation of the robot, right? If you worry about how the robot is directed at the goal state, then you have to include the orientation of the robot as well in this configuration space. So we need a data structure. We need a way to represent this occupied and free space from the robot's perspective. So for example, a configuration space in its most simplistic form for the navigation problem can be the 2D plane. And if you assume that the robot is a point, and that you don't care about the orientation, then you are just dealing with the XY positions or the rectangular positions of the robot in this space. So you have the entire configuration space. This is basically wherever the robot can go, and then there are regions of the configuration space that are occupied by obstacles, which are the shaded regions, and then there's this free configuration space for the robot to navigate. What if the robot is not a point? And this is actually a good point, because no robot is a point. Then what we do is we inflate, we expand the obstacles so that we can shrink the robot as a point. We can reduce the robot to a point for representation and algorithmic from an algorithmic point of view. So this is very straightforward, because we know that we know the dimensions of our robot, and then if you simply expand your obstacles, then you can assume that your robot is a point and you can navigate. So let's look at an example. As I said, we'll try to understand what a very simple algorithm that's called Wavefront Algorithm for path planning. And I already gave you an idea about what's coming. So typical simplifying assumptions for an indoor robot will be, we assume that the world is flat. So a 2D representation is sufficient. Robot is round so that the orientation does not matter. And robot is holonomic. That means it can move in any direction. For the case of let's say certain types of robots, this may not be true. You may have to make the robot turn first and so on. But there's some reading assignment on this view constraints, which will guide you through what we mean by robot is holonomic. But we don't care how the robot moves; it can move in any direction for this case. So what we do is we look at a top-down view of our space. So this is, let's say, a one-bedroom apartment. You have the entry point, and then you have the bedroom. That's your start. And then what we did was here, we took the size of the robot and enlarged our walls and obstacles. So the shaded gray is where it is. And then what we do is we overlay an occupancy grid on top of this map. Right? So what we say is that, okay, for the sake of navigating, let's just put down a grid on the map. Now, what happens all of a sudden is that we have an understanding of where the free space is, not only in terms of continuous space, but in terms of this grid. This is a much better representation of the world for algorithmic purposes again. So then what we do is we account for the configuration space, right? So if you go back to the previous one, you see that some squares have certain sections of the obstacles. We want to avoid those, right? So we want our robot don't go into those squares. So if you take that into account, all of a sudden your world turns into this from the robot's perspective. So again, starting from the start and going to the goal, the idea is to find the path. Now we have to make certain assumptions, and let's talk about the Wavefront algorithm now, more specifically. The idea is the map 4 connected or 8 connected, right? So in the 4 connected map, you can only go north, south, east, and west. In an 8 connected map, you're allowed to go in the diagonal direction as well. But then what happens is, to be able to connect this to the example that we started, the center of each physical square now becomes a node for our purposes. So let's see how the Wavefront algorithm goes. What we do is, let's say we have this start somewhere here, and we want to get to the goal. Now, if the robot is at the goal, that means you're ground zero. You're at, you don't have to make any effort to get to the goal. So we start from the goal and we look at, assuming a four connected map, we look at, okay, what are the distance one squares, right? Grid cells. Where can the robot go? Where can it be in this map so that it can get to the goal in one step? And these are the labeled on the iteration. And what we do next is we look at, okay, now expanding on this wavefront as if you dropped a little pebble at the goal. Now we look at, okay, so what are the grid cells where the robot is of two distance, right? In two steps from those points, from those grid cells, you can get to the goal. You do the same thing for 3, and then you do the same thing for 4, and you continue to do this until you get to the last, until you hit start. So all of a sudden, you know a lot of things. What you know is that you are 5 steps away from the goal for the specific example. And then by simply following a decreasing number of orders, you can create a path, right? So from 5, you preferably go to one of the four cells, and then 3, 2, 1, 0, and then voila, you created a path. So the lesson is organized in such a way that it introduces you to a number of terminology that I skimmed through in this presentation. You will have certain reading sections. It should be pretty straightforward. And then there are a few videos for you to watch and enjoy, and happy learning.